every time your car crashes into a wall in a 3D racing game, your console just solved, like, millions of invisible geometry problems in a fraction of a millisecond.
Yeah, it's honestly mind-blowing when you really think about it.
Right. So today, we're looking at the secret code making that happen. Welcome to today's deep dive into a presentation called Vector Quest.
And we have a very specific mission for this one.
Exactly. We're taking the complex math of vectors and using the Feynman technique to, break it down so simply that a 12-year-old could grasp it.
And show the real-world magic it unlocks. So a vector at its core is, well, it's basically just an invisible movement instruction.
Okay, an instruction.
Right. It only cares about two things: how far you go, which is the magnitude, and which way you head, the direction.
So it doesn't matter where you start on the map.
Not at all. Only how you move.
Okay, that makes sense. But the presentation brings up this puzzle called the crossroads problem, which is, well, how do you multiply two directions?
Yeah, because in normal Mac, 3 times 4 is 12. Easy.
Yeah. But you can't just multiply the lengths of vectors.
No, because the way they point fundamentally changes the whole outcome. So mathematicians had to invent entirely new ways to multiply these arrows.
And the first tool is the dot product.
Right. Think of it like a teamwork score. If your virtual car is driving forward and a heavy wind is blowing.
Like pushing a minecart on a track with your friend?
Exactly, like 2 players pushing a minecart. The dot product calculates their teamwork. It asks, how much are these two forces working together in the exact same direction?
And it crunches those arrows to spit out just a single number.
A single score, yeah, a scalar.
I really loved the flashlight trick analogy they used for this to explain it to a kid.
Oh yeah, the shadow trick.
Right. If you shine a flashlight straight down onto those two arrows, the dot product is just the length of one arrow's shadow multiplied by the other.
So if the wind is perfectly behind your car, the shadow is huge.
Maximum teamwork.
Exactly. But if you're driving forward and the wind hits you perfectly sideways, like at a 90-degree angle,
that flashlight casts absolutely no shadow forward.
0 shadow. The teamwork score is 0. Mathematicians call this being orthogonal.
Orthogonal, which is really just a fancy way of saying those two forces have absolutely zero effect on each other.
Precisely. And game engines use this exact shadow mechanism for lighting.
Oh, wait, really?
Yeah. If you shoot a digital light beam at a flat wall, the dot product calculates the exact angle they meet. A direct 90-degree hit is maximum brightness.
Ah, and as the angle changes, the teamwork score drops.
Right, which tells the game engine to smoothly fade that spot to a realistic shadow.
Okay, so the dot product gives us lighting on flat ground. But here's where it gets really interesting. How do we escape the flat map?
Right, because we want to build a 3D wall. We need a way to build straight up.
Which brings us to tool number 2, the cross product.
Yeah, the dot product gave us a flat number score, but the cross product takes 2 flat arrows and creates a brand new arrow pointing straight up or down.
It literally creates a new dimension. To explain this to a 12-year-old, the presentation uses this tent pole analogy.
I love that one. You lay 2 flat arrows on the ground, and they form the edges of a flat shape, like a tarp.
And the total area of that flat tarp equals the exact height of your new 3D arrow.
Shooting up like a tent pole.
But wait, I'm kind of stuck on this. If I lay a tarp on the ground, a pole could stick up into the sky, but couldn't it just as easily dig straight down into the dirt?
Yeah, it absolutely could.
So what stops the math from guessing the wrong way? Like, does the order matter?
Order completely dictates the direction. And you solve this using your own hand, the gamer's hand or the right-hand rule.
Okay, how does that work?
You point your index finger along your first arrow and your middle finger along the second arrow. Your thumb will naturally stick out in the direction of that new 3D arrow.
So if I flip the order, multiplying the second arrow by the first, I have to, physically twist my hand upside down.
Yep. And now where's your thumb pointing?
Straight into the dirt.
Exactly. Flipping the order flips your reality upside down. In regular math, 3 times 4 is 4 times 3. But here, flipping the order reverses the direction entirely.
That is wild.
And this twisting motion isn't just theory either. Engineers use the cross product to calculate torque.
Torque, like twisting force.
Right. It's the math behind the twisting force when your virtual car's tires grip the asphalt and propel you forward.
Or when a drone's propellers spin to lift it off the ground.
Exactly. So whether you're measuring how forces align with the dot product or, twisting into new dimensions with the cross product.
These invisible arrows are the secret architecture of the world around you.
They really are.
It leaves you with such a staggering thought because, like, a single cross product calculates the torque of just one wheel.
And one dot product calculates the shadow of a single light beam.
Right. So just imagine the sheer volume of invisible arrows, intersecting shadows, and twisting forces that your computer has to perfectly calculate every single millisecond.
Just to let you drift around a single corner.
Yeah, in a simple 3D racing game, it's incredible.